Will provide just a few highlights of the major atomic theories that have led to our current atomic model. The idea of the atom dates back to ancient Greece, where Democritus and Leucippus are credited with one of the first atomic theories way back in the 5th century BC. Think about how much ancient Greeks must have thought these guys were complete weirdos. The thinking at the time was that elements were earth, air, fire, and water. There's a constant quality to all of these. The air around us feels like a collection of particles, but not a single particle. The water we drink flows freely as a unit of many molecules and not a single one, etc. It had to be quite the departure for the Greeks to think of individual particles here. There are some solid parts to their theory. For instance, they said that matter was composed of atoms separated by empty space through which those atoms move. This is true for gases, and if we don't split hairs about what they meant by empty space, it's true for most samples. Because unless we're at a temperature of absolute zero, or 0 Kelvin, the particles in our sample will at least wiggle in place. They stated that there are different kinds of atoms which differ in size and shape, which is partly true because the more subatomic particles an atom has, the larger it is. And there are other tenets that are also at least partially true. Not too bad for the 5th century when the Romans were eating off of lead plates. John Dalton was a British chemist and physicist in the late 1700s and early 1800s. More importantly for us, he was the first person to say, "Hear ye, all atoms of a specific element are identical." Honestly, I legit have no idea if he said hear ye, but I like to think that he might have. In addition, Dalton said that if an atom wasn't identical to another one, then it had to be a different element. This wasn't entirely correct, as we later discovered ions and isotopes, but these statements laid the foundation of our modern atomic theory. In terms of the atoms themselves, Dalton thought that they were solid, indivisible spheres that couldn't be broken down or destroyed. The last part is correct, they can't be destroyed. The first part, not so much. But given experimental methods in 1803, he actually came extraordinarily close. J.J. Thomson was a British physicist who discovered the electron in 1897. This discovery led to a shift from atoms as solid, indivisible spheres to species that had charged subatomic particles spread evenly throughout that sphere. Thomson's atomic model is often referred to as the plum pudding model. This is because he believed that an atom was actually a positively charged sphere that had electrons distributed equally throughout it to keep the atom electrostatically stable, or just think neutral. This meant that there was an equal chance of pulling an electron out of that atom at literally any spot in that atom, kind of like there's an equal chance of pulling a plum out of any spot in a plum pudding. Yes, I know you've probably never had a plum pudding. I haven't either because this isn't the turn of the last century, but you can use those imaginations. This model helped to explain the existence of our electrons. After all, we didn't know what protons were yet, so the solid positive sphere wasn't that bad a guess. It also helped to explain why our atoms are neutrally charged overall. Thomson won the Nobel Prize for this work in 1906. Still discovering physics things in England, though this time the scientist was actually born in New Zealand. Ernest Rutherford's gold foil experiment is one of the single best examples of brilliant experimental design based on a truly reasonable hypothesis that still went slightly awry, and then was still revolutionary. Rutherford passed positively charged alpha particles, more on this in 117, through a piece of gold foil. The majority of the particles passed right through that foil unfazed and hit a detector directly in front of the lead box holding the radiation source. These points were easily explained by stating that the atom was mostly empty space. Second set of data points, which were deflected backwards from the foil, were also relatively easy to explain because these probably had to hit something so dense that they bounced off of it. What was tricky were the data points that were deflected just off to the side. These were unexpected, and Rutherford had to adjust his initial hypothesis to explain them. He eventually determined that his positively charged alpha particle beam was traveling very close to something else that was positively charged, a repulsion occurred, and thus the beams were deflected. Very cool stuff for the year 1911. And thus, the Jimmy Neutron model of the atom was born. As you can see, it's mostly dead space with a positively charged area in the center. This model led to a better understanding of not only the charge distribution of the atom, but also the mass distribution. The nucleus as we know it today still hasn't been explained since the neutrons weren't discovered for another 21 years, but this was a big step towards that. Just a few short years after Rutherford's very kick-butt gold foil experiment, Danish physicist Niels Bohr improved Rutherford's theory, stating that our electrons arrange themselves around the nucleus in distinct shells. He combined the idea of the nucleus that Rutherford proposed and the regular spectral patterns emitted by hydrogen atoms. Imagine having that guy as your physics professor. Bohr's model was so revolutionary because it was the first to utilize quantum theory, read very complicated math. It was the first step towards the Schrödinger model that we've landed on today, as it helped to explain how atoms absorb or emit radiation when electrons change energy levels. More on this in Module 5. And now we come to the cat guy. The Austrian-Irish physicist Erwin Schrödinger adjusted Bohr's model in 1926. He calculated the probability of finding an electron in a specific area around the nucleus using an equation that he developed, aptly named the Schrödinger equation. This model utilizes the wave-particle duality of our electrons. Bohr assumed that the energy of electrons was quantized, though he had no mathematical proof. Kind of like I assume I am a delight, despite not having any proof. Schrödinger helped to prove Bohr's model mathematically, so they're compatible in that respect. They differ in the restrictions placed on the movement of our electrons. Bohr limited movement of the electron to well-defined circular paths around the nucleus. Schrödinger's model differed wildly from this by giving the probability of finding an electron at any point around the nucleus, not just in certain orbital spaces. As an aside, what a unique human you have to be to describe the quantum mechanical nature of energy states using an analogy where there's a cat that is either dead or alive in a box, and you don't know if it's dead or alive until you open that box.